Yeah, I believe that you are familiar with the 7-layer protocol, right? Even with the network communication, you probably should learn these stuff. So, did you learn that 7 layers protocol? So, OSI protocol, that layer, this one. So basically, hypothetically, uh, engineers develop that hypothetical layer like application, presentation, session, transport, network, and data link and physical layer. This is kind of hypothetical setup for the network communication. But some protocols. So basically, in the practical implementation, we are not implement all 7 layers. It's like considering couple of layers, people have invented some protocols. So all the information are here, like what are the protocols that we are using, and description and the in which layer that these protocols have used. Like as I remember, we have looked into that one. Uh, so I will jump to the routing part, since in the exam you sometime there will be a question regarding the routing, and you have to configure the routing table, right? So basically in routing, when you're looking at the network setup, uh, that communication has happened through that routers. So in order to transfer some packet from a source to destination, it will traverse through a couple of routers. So in that case, in order to find the correct path, so it look into the router configuration or the routing tables. So in such cases, we have to configure in early days. Actually, we have to configure the routers, but nowadays the router itself has the knowledge to identify the underlying infrastructure and update the routing tables, right? So, but as engineers, we need to have a kind of a knowledge on routing tables, right? So this is a kind of a small example. So even I have given this example as a question in the exam as well, right? This time as well, there can be some similar questions from this section, right? So assume that we have 5 hosted networks or local networks, right? Likewise, 1, 2, 3, 4, 5, right? So these hosted networks are connected through again 5 routers like A, B, C, D, E, and in between the routers we have the links. So two routers get connecting two routers, it creates a link, like link 1, 2, 3, 5, 6. Likewise, in between all the routers, there can not connecting all the routers, like there can be two routers connected together and create a link, right? So in each and every router, we can see a routing table, right? Since we have 5 routers, that means we have 5. So in each router itself, they are maintaining their routing tables. So if you look at the routing table for router A, this is the routing table for the router A, and this is the routing table for the router B, and likewise C, D, E. Since we have five routers, that means themselves they are managing uh, their routing tables itself. Like with this given examples, there will be 5 routing tables, right? So if you look at the first router, router A, so this is a respective routing table, right? So in once we connect a router, into the network. In that routing table, it will keep three kind of configuration, right? Like connected, it try to keep a reference for each and every router in that network, and in order to route into the respective router, what is the link need to refer and what is the cost available, right? So in routers, they continuously monitor the network and using some algorithm like Bellman-Ford. So they update the routing tables, right? So if we take an example, in this network setup, we have 5 routers, A, B, C, D, E, right? So we have A, B, C, D, E routers. So we try to configure the routing table A, right? So through that routing table, it can connect to the router B, router C, router D, and router E, and itself, since in that network we have 5 routers, A itself managing the routing table, right? So we have A, B, C, D, E routers, and when we consider routing table A, so if we check the connection between router A to router A, it's there won't be any link. Actually, it's a local connection, right? It refer itself, right? So then that means there won't be any cost, right? So because of that, it refer the same router. But when we look into that router B, right? Router B, from A to B, so we are talking about router A. In order to route from A to router B, there can be lot of paths, right? So this will be a one path, this will be another path, this will be another path. Likewise, there can be lot of paths to connect with router P, right? So as I said earlier, so basically in updating the routing table configuration, they have referred some algorithms like Bellman-Ford pathfinding algorithms, right? Shortest path finding algorithms. So referring that kind of algorithm, they find the lowest cost path in order to create that connection, right? So when you're looking at that cost, if we try to clarify the cost, that means how many routers, or how many links that we need to pass in order to find the destination. So in cost, when we are talking about the cost, it refer how many links that we need to pass through at the time that packet is delivered to the respective router, right? That's the idea. So when you're talking about the router, that connection between the A and B, whether it can go to the link 1, or link 3652, or link 364, likewise. Even there can be multiple stuff, right? Even there can be link 364, yeah, for it's sometimes there can be some configuration, likewise CF, likewise there can be multiple ways to go through the router A to router B. But when in a routing table, it try to find the shortest path. So that's the idea, right? There can be multiple connections or the multiple paths to deliver that packet from router A to router B. But in the routing table, it consider the shortest path. So that's the idea with the routing table managing, right? So it look for the shortest path in terms of number of links that packets need to transfer in order to go to the respective router. So that's the idea. right? We have in with this example, we have three possible paths: A to B, ADEB, or ADECB, right? When we look into that cost parameter, here cost is 1 from A to B, but for the ADECB, so 1, 2, 3, 4, we are passing 4 links, cost would be 4, and for this one ADEB, link 3, 6, 4, so cost parameter would be 3, right? So referring that Bellman-Ford algorithm, so basically it picks the shortest path. So in this case it picks this one. So because of that, from link A to B, it find the link, it refer the link 1, right? It refer the link 1, and cost would be 1, right? So again, I'm looking to that another router. Let's look into that router C. When you're looking at the router C, this is the router that we are looking at, right? So for that routing a packet from router A to C, so that can be happen through this path. We can happen through this path. It can happen right? There can be multiple ways like this, right? So if we consider the cost for each and every possible path, for this one it would be 2, for this one 1, 2, 3, it would be 3, for this one 1, 2, 3, 4, for this one 1, 2, 3, right? So we have possible paths, 4 possible paths. One is cost will be 2, 4, 3, and 3, right? So then we will pick the shortest path where cost would be 2. We pick that one, and so there's an interesting thing. So we consider the close, the most close link with that respective routing from A to C, right? So let me explain that one again. So for that one, this is A and this is C. This is our source, and we are looking at the destination C, right? So we have selected this path since it has the shortest, the lowest cost or the shortest path. In order to go to that direction, router A should redirect that packet to the router B, intermediate routing, right? So because of that, we have to choose the link 1, right? That's why we pick the link 1. So when considering from routing from A to C, take that path, we have to pick the link 1. So we have configure link 1, and we have given cost would be 2, right? So likewise we can update the respective routing configurations. Even for the D and E as well. right? If you look at the routing from A to E, routing from A to E, again there can be multiple possible paths, like this path, this way, or this way, right? So with this one, cost would be 2. This way, this cost would be 3. And for this one, again, cost would be 2. So this case, you can find, since we have, when we pick that algorithm, right? So it will provide the shortest path. So in this case, we have two possible uh, cases, right? Picking the link 1 or picking the link 3, right? So it depends, right? You can pick link 1 or the link 3, right? In order to transfer that packet to from router A to router E, right? So you can even select that path or this path, but in both cases the cost would be 2, right? So we're talking about the E, so cost would be 2. You can pick either link 3 or link 1. Here with that example it has given link 1, so that means they have picked this path, right? So in such so likewise you can update all the routing tables, right? You have to think about the shortest path or the lowest cost uh, when you are picking the correct link, right? That's the main thing that you need to concern about the routing. So you can try out yourself, and you can check whether you can uh, find kind of a similar routing table with the given example. Any questions? Any questions regarding the routing tables? Seems no. Right. Okay. So in so as example, I have given same example, but with some changes, right? Breaking up some links. So then how routing tables get updated in such scenario. I believe that you have tried out that one, right? So next week, if you need to discuss the answer for this one, so I can set up. So before starting the lecture, we can discuss, right? So are we going to start the next presentation? As a fourth lecture, today we are going to talk about the inter-process communication, right? So even though we are talking about the communication, like it's actually communication in between the processes, right? So that's why the title says as a inter-process communication. Basically, we try to understand the UDP and the TCP protocols here. Are you familiar with the UDP and TCP? Yes or no? Raise your hand if you know UDP and TCP. In your Zoom, there's an option called raise hand. Hello, can you hear me? Okay. You are not familiar with the UDP and TCP, right? Some people say they don't know, and some people have raised their hand. So what would be the answer? Anyway, so we will try to understand the UDP and TCP here, right? Uh, so in UDP we will refer datagrams, and TCP we are using stream. So we will discuss these things, right? So basically in the interprocess communication, basically we are talking about two operations, right? So in message passing in between these two processes, right? So in order to communicate with in order to communicate some messages in between two processors, right? So we are talking about pair of processors, right? So in this pair of processors, we that message communication operation are defined as a send and receive, right? We have two operation. One process is sending something, and another process is receiving that information. So that's the interprocess communication. We are talking about send and receive operations, right? So in terms of transferring message from from one process to another. So that's the basic idea. So you know the basic idea of the sending and receives, as the term says, to communicate. So one process is sending a message to a destination, and that destination basically receive that information from that sender. So that's a uh, operation available in that interprocess communication, send and receive. That's a normal idea as you have, right? So when you're talking about that send and receive, and even with interprocess communication, right? I believe that you are familiar with the term synchronous and asynchronous communication. Do you? Do you familiar with synchronous and asynchronous communication? Okay. One person knows about that one. What about the rest of the people? Asynchronous, synchronous. Kesha knows. Two. The people who have worked with the front end application development, I believe that they are much familiar with these concepts, right? Asynchronous and synchronous. So when you're talking about interprocess communication, basically we are talking about processes. I believe that you have learned the operating system and you know the meaning of the processor, right? Even though it can be two different host machines, right? Or even it can be reside in the same entity or the same machine as well. But we refer processors since they are separately executing, right? It can be communicate over the network, uh, which are connecting two end nodes. Both processes are executed in two different end nodes. So sometimes these processes can be executed in the same uh, infrastructure of the computer as two separate processors, right? Communication has happened through the underlying hardware or the network layer, right? So when you're talking about the interprocess communication, give me 1 second. Sorry about that one. So when we are talking about the process communication, mainly there are two things: synchronous and asynchronous, right? So let's try to understand what is synchronous communication, right? So when you're talking about two processes, sending process and the receiving process, in a synchronous approach, so one that sending process and the both receiving process, they are blocked in between that operation, right? So sending process is once that send is issued by the sending process, that process is blocked until the corresponding received process is received that message, right? So that means that received process, it should issue that received message once it receive the information. So until that acknowledgement received, basically that sending process also get blocked. So that's a synchronous. So sending process execute the send task, and that program blocked at this point until that process received the received message from the received node. So that's the idea. Let me draw something. Let's see. Let's assume that we have in our program we execute something and we try to send some content, and we have send that information, and in our program we need to execute some execution event once we executed the sending message, or once that sender issued that send action in that program, there can be some other execution needs to be executed throughout that program. But in a synchronous communication, this is the place where that sender execute that sending message. So so it will transfer to the it will received by that message will received by the received process, and that process should issue a received acknowledgement or the received message. So it's like ensuring the receiving of that message into the sending process. During that time, there won't be any execution in that user program. Basically, that sender also get blocked during that time, and even the receiver itself waiting for some request. So when you are looking at that sender as well, receiver as well, so basically uh, the sender will wait on some request. Actually, it's waiting on the request until it receives some request that receiver get blocked on that process. So that's the idea. Both receiver and the sender, they are both blocked in the communication in the synchronous, right? But when you're talking about the asynchronous communication, since that sending party, once that they are ensure that once that sender is done with the sending of that message, so that sender is not interested on the receiving message, he can continue on his task. The sender can execute his respective task other than blocking on the receiving status, right? In such cases, we are using asynchronous communication. In such cases where that sender is not interested on the receiving part, right? Ensuring the receiving. So basically, sender will issue a sending message, and it's like it's that sending part will take care of by a separate thread, and sender will look into that respective execution. And uh, if that sender is interest on the receiving part or some responses, uh, once that sender receives some received message from the receiver, so then it's like a interrupt handling kind of thing. So then sender can pause some point and will can take care of the response coming back from the receiver, right? So that's the idea. Like normally in the asynchronous communication, sender will not block on the receiving, and that sender will not interest on the receiving part. He will that process will start continuously work on that execution. And it's like we are handling that like handling interrupts in the operating systems. Once that receiver issue a receiving message, so then again that sender will look at the respective execution based on the message received from the receiver, right? So these are the two things. uh, in a synchronous, both sender and receiver, they are executing the same, uh, so they blocked in between each other. But in the asynchronous communication, sender will not block. Even we can come up with some mechanism to for the receiving party as well. But when you're looking at the actual implementation, we rather interest on uh, 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 asynchronous communication and unblocking in that sender. So sender is the person who doing some is the process which does that meaningful stuff for some logics. So then basically server or that receiver is fulfilling some requirements. So in that kind of setup, basically non-blocking part should address in the sender. So because of that, uh, we mainly go with asynchronous communication when considering the asynchronous communication from sender side, but will not rather interest on the receiving party, right? When you're talking about the interprocess communication, we need to focus on the message destination, right? So message destination does not mean that just only the IP address of the or the physical address of the destination node. It's kind of collection. It's a collection of port and the destination address. So that's the destination, right? So in the internet protocols, uh, when you're looking at the computer setup, we have 2 to the power 16 possible ports, right? So in a hardware layer, it supports 2 to the power 16 possible ports, 65,536 or something, right? So in 2 to the power 16 ports available in the underlying hardware layer and operating system level, they support these number of possible ports, right, in order to communication. So that means in a computer, there can be multiple applications executed, right? So that's why they have come up with that port concept, right? So if you consider one single application, one single machine, so when we connect that machine into the network, so it's technically it's received a one IP address or the physical address, right? But at the time we need to execute multiple application in that computer. So then if you particular bound with that internet that IP address or that physical address of that computer, so then we rather can communicate with one process at a time, right? So in order to resolve that one, so that's why we are having that 2 to the power 16 possible ports defining the operating system level and hardware level, right? That means with a single machine we can possibly execute 2 to the power 16 services, right? Where we can extend the use of our computer or the system, right? So that's why when we are talking about the message destination, we talk about the internet address and the port. So combination define the destination, right? So if it is so you are familiar with the HTTPS communication, so then if you just do a port scan in your computer, so then you can see lot of ports are communicate with couple of couple of services, right? So in your browser, your browser process communicate with some external resources through the HTTPS communication through that port 80. And if you just uh, use some SSH to another computer or another server, again same machine, right? But you connect through the port 22. Likewise, so each and every process which define allocate with the port, so together we call it as a message destination. So that's why that pair of that internet address and the local port define the message destination. And when you're talking about the interprocess communication, we have to concern about the reliability, right? So when you are talking about the communication, and we know that that communication can happen uh, over the network, and we will that message will reach to some remote uh, processors, right? So in such cases, in interprocess communication should provide the reliability, right? So in between the communication, there can be some there can be some situation where that message drops or the lost, right? So we know in the previous lecture we have identified that packets are transferred through the network and they are traversed through that routers, right? So due to some bad routing configuration, there can be a situation where that packet get lost, or some due to some issues that packet can drop. Likewise, so when you are setting up a network, we have to set up a network which ensure the reliability. And since that again when you're talking about the reliability, again we have to talk about the integrity as well, right? So integrity, that means that message should not updated at the during that transition time, right? Like when a process A sends some message to the process B, that message, that processor B should have a way to ensure that that message process B have received is not corrupted in between the communication. In such cases, we are using that checksum mechanism, right, which ensure that we have received the actual content as sender sent. Likewise, so then in such cases we can use the checksums. And another thing is ordering, right? So we are sending messages, but we have limitation in our network. We cannot send all the content through the network as single message, right? So in such cases, and even there can be uh, communication back and forth within the two processors. In such cases, messages are communicated in between that two processors, and they are that order of that order, or the sequence of that messages plays a important part. So in such cases, we have to deliver that messages in a correct order, right? So otherwise, there will be an issue with the content that two press there can be an issue with the receiver as well, right? So since that order is uh, not in the correct sequence, right? Let's assume that we are in a kind of a just think about the chat application, right? So in such cases, what will happen if that order is not in a correct form? So receiver will see the messages at the time that application receiving application receive the content, but if there's a problems happen in the network, so sometimes an order will not in the correct sequence as sender send. So in such cases there should be a way to create the correct sequence, right? So at the time we need to ensure that the ordering, so there should be a mechanism to uh, there should be a mechanism to ensure the order, right? So likewise, so we have these concerns, right? So in application development we basically talking about the sockets, right? So you are familiar with the socket communication, and the people who did some front end application development, I believe that they have referred socket.io. Likewise, in application development we talk about sockets. When you are talking about interprocess communication, we talk about the physical internet address and the port. But when you're talking about the application development, we rather talking about sockets, right? It's again like socket is defined with the port and the destination address or the internet address. Combination define the socket, right? So socket, uh, as we discussed earlier, when you're talking about the destination, it's a pair which is internet address and the local port. So basically in application development we talk about the sockets which concern about the internet address and the port. Here as you can see we have the 2 to the power 16 possible ports, right? So likewise when we consider in the combinations, and when in the standard communication in standards, even though we have 2 to the power 16 possible ports, there are some restriction, right? There are there is a portion reserved for that predefined applications, like port 80 for the HTTP communication, port 22 for the SSH communication, 23 for the telnet. Likewise, there are a couple of, as I remember, 1000 to 1023 ports. First 1023 ports are reserved for well-known application, and rest of the things we can manipulate, right, with our purpose. So that's the idea. Even though we have 2 to the power 16, first, as I remember, first 1023 ports can be used with our reserved for the well-known applications, and rest of the ports can be used with our use cases, right? So sockets basically talking about the application development which abstract that underlying communication, right? So socket is defined with the uh, source address and the source port, or the port and the address, right? The combination define the socket. And so for the application development we use sockets. So when you're talking about that protocols which define on top of that sockets, we simply can understand the UDP datagram communication and the TCP streaming communication, right? So UDP basically UDP connection is defined as a connectionless communication, and TCP defined as a connection oriented protocol. UDP is a connectionless protocol, and a TCP is a connection oriented protocol, right? So in a UDP, so in a UDP communication, we transfer datagrams, right? That's why we define as a UDP datagram communication, right? In a UDP protocol, we transmit that message through the datagram, and the datagram is transmitted between these two processes. And as we understood, one process send that datagram and another process will receive that datagram, right? In order to communicate that datagram in between that sender and the receiver, it will refer internet address and the local internet address of the host machine and the port, right? So socket is directly bound with that internet address and the port, right? Referring that host address and the port, that communication will happen. So in UDP, basically, I will draw another diagram. Let us assume that in the UDP, we have process A and process B. Right. So let us assume that we have an infrastructure like router A, router B, router C likewise. For your understanding, I will just use A and B processors. This one will be sender and this one will be the receiver. And we have three routers like ABC, right? In UDP communication or the UDP datagram communication, basically it's a connectionless communication, right? That means in that UDP protocol definition, it won't try to create a connection between the A and B, right? That UDP protocol, it does not try to create a connection between A and B, right? It's rather A sends a datagrams continuously and B will eventually receive the datagrams, right? But that UDP protocol does not try to make a connection. Connection means that making a path, right? It's like this. Let us assume that we have sequence of information needs to pass in A, 1, 2, 3, right? So these are the datagrams or the messages that A needs to send to process B, right? So basically A takes that datagram and attach the receiver, destination, host B and the port, right? Right. Let us say that we are going to pass that datagram 1, 2, and 3 from A to B, right? So A is the sender and the B is a receiver, and we have a infrastructure like routing configuration like ABC. I think I can. Right. So let us say we try to send message 1 first. So in datagram, it define. So let us say we are communicating through the port 80, right? It says that B with port 80 going to send that first message and attach the A. Let us say that it's a 5000. Right. So we define that datagram. This is a datagram, right? So not just the message. In the datagram, it has the receiving information and the sender's information. So receiver or the destination. So it's sent to the B. So physical address of the B and the port, right? Even with that datagram, it consists the physical address of the sender and the respective port, right? So this packet, first packet will transfer through from A, B, and C, right? But in the next round, for the second message, it will take a different path, right? It will transfer through A, C, B, and go to the destination, right? So that's the idea of connectionless, right? So you need in advance, to make that communication in between the process A to B, UDP does not create a connection. It just, so basically that datagram, it's find the route and reach to the destination. So routing will happen in the network and that datagram packet will reach to the destination, right? So it does not mean that all the packets will transfer through the same routing, same routers, right? In a UDP, it does not make a connection. Basically, it attach the destination information and the hosting sender's information and just uh, let that network to handle itself in the routing part, right? And like it's infer that that datagram itself find the path into the destination. So that's the idea. So basically A or that sender just send a message. So then onwards, that protocol, so that UDP datagram itself find the path and reach to the destination. So that's the idea, right? So in a UDP, that's the idea. It does not create a connection in advance between A and B or the sender and the receiver, right? So that's the idea with the UDP. So when you are talking about the UDP, So these are some issues related with the data UDP communication. So message size, right? So since we are talking about the transferring messages in between two processes, right? So we have to define the size of the message that we are transferring, right? So if it is if so in a communication, in the network communication, it define the maximum size of data that network can handle, right? So because of that, uh, that message can reach the existing or the given maximum size of the data, or sometimes it can be lower than the maximum size, right? If that message is exceed the given size of that message size, so then it has to chunk into couple of messages. So then it should pass the related information with the UDP datagram. Like if that that message is chunked into 3, so then that UDP datagram should ensure that the receiving party receive the same amount of packets, and that order should be managed. And likewise, finally, that receiver also should recover the correct message from the message received at the receiving end. So message content is message size is another concern, right? So with UDP communication, we have a challenge with the message size, right? And as we discussed, blocking and non-blocking. So normally in socket communication, it's provide the non-blocking sense, but in the receiving party, uh, there can be some blocking scenarios. Normally, uh, in application development or the communication, we interest on the non-blocking sense. And so in the receiving end, we manage queues in order to reduce that burden at the receiving sides. And even the since that we have discussed about that blocking and non-blocking scenario, and again I have communicated that we rather interest on a non-blocking sense, but at the receiving end, so that process that we are not concerned about the non-blocking state of that processes of the receiving end. That means at the time we are sending some information from sender to the receiver, the sender can block on some previous task or the previous message which it has received, right? In such cases, we have due to that blocking consideration, the packet can be lost. So because of that, in order to ensure that that packet has delivered to the respective sender, we have to come up with the queue mechanism, right? So where that that's that receiver will receive that messages, even the receiver is blocked on some ongoing task, right? In a queue, it continuously queue the received information or the datagrams. So then it's guaranteed that data will not lost at the time that receiver is blocked on something. And here we have timeouts, right? uh, Timeouts mean that since we don't have any uh, pre-configured connection in between the sender and the receiver, sometimes that packets may get lost over the network. So then we have to set up timeouts, since that's that processors will uh, depend on the uh, sending or the receiving datagram, right? So then that servers will wait on the receiving request, right? So because of that, sometimes due to the network setup, uh, messages or the data can be lost in the network. Because of that, in order to provide the responsiveness with the processors, they should have a timeouts configured. And since that datagram have that information about the sender and the receivers, they can receive any message from anybody, right? So basically, receiver, they are open, so senders can send messages to the receivers. So basically, in the UDP communication, they attach the sender's information. So when you're talking about the failures in the UDP datagram, right? We are mainly talking about the integrity and validity. So main concern with the UDP communication is that message lost, right? So due to some problems with the network, sometimes since since that communication does not make a connection in between the receiver and the sender in advance, that some packets or the datagrams can be lost in the network because they route themselves. So in such cases, message may be dropped occasionally, and that messages even get manipulated at the transmission, right? And sometimes that messages can be lost due to the buffer overflows, like no space available in the buffer in the receiving party. So in such cases, since that UDP does not concern about the receiving acknowledgement, rather just sending the content or the message continuously. So in such cases, since that UDP protocol does not interest on the acknowledgement from the receiver, that packet may lost. So let us say that process B is that queue of the process B is fully occupied with the datagrams. So the next datagram which reach the process B, so since there won't be any space in the queue, so technically that message get dropped at that point. But in a UDP communication, that receiver sender does not interest on the receiving acknowledgement. So because of that, sender does not know about the drop of that message. So that's the main thing. So omniscient failure. So sender does not know about the message loss or the drop of that message. And since that since that communication is not prefer a pre-identified route or the connection, so then some packets may use short paths. Sometimes some messages may use some long paths in terms of the routing, right? So then that arrival time will be different, right? Even with the first message, it will arrive the destination after the second or third messages. Likewise, since that UDP connection does not make a connection in advance, because of that datagram itself routing, so that ordering can be different, that receiving time can be different. Because of that, in such cases where that ordering is interest, basically that ordering should maintain. So because of that, we have to, so there will be an issue with the ordering as well, right? So but still we are using UDP in some use cases, like domain name validation, right? We just in browsers, we in order to resolve the IP address, so we rather communicate with the domain names, but the domain names are reside in the domain names servers. So that domain name servers, they resolve the IP address on behalf of us. So basically, if we just press facebook.com, basically in domain name server resolve that facebook.com, and find the IP for on behalf of us. So basically it has the mapping for this name. This is the IP address likewise. So then browser make the connection with the IP. So with that domain name systems, so they just rather interest on the communicate that message. So they use the UDP protocol and voice over IP, like Google Hangouts or some kind of video streaming mechanisms application, they use UDP, right? Real-time data transferring is the concern, right? So such cases they use the UDP. So here I have referred a UDP implementation. You can look at that Git repository, right? Under the lecture 4, I have created that sample UDP implementation from Java. Right. So this is a UDP client. So in that Java itself, it's provide that same interface, datagram concept, right? So we are going to communicate through a socket, right? So that means we are going to use in Java implementation, I have created the datagram socket since I'm going to use a UDP, right? So when you are creating a datagram packet or the datagram, so I include the message and have to define the size. This is the size of the message and who is the destination and the respective port, right? So then I basically send, this is the send process, right? I asked to send that request. In a server implementation, again it's basically create a datagram, right? Referring a buffer, right? So this is the queue, right? So we create a buffer and we create a datagram based on the buffer size, and we send that received acknowledge. So basically we receive the request. So this is the received, and for this example I have created an acknowledgement message which sent to the client, but it's not a mandatory thing, right? So I have purposely built the acknowledgement here, right? So basically you can execute that one for your reference. Referring the Java, I have given the implementation for the UDP client and the server. So I can execute that one. First I need to start server. Then I'm going to start the client. So basically I send the first message to the server. So it has received, and the size 40. And since I purposely send a acknowledgement, so client received the acknowledgement here. So in order to understand the communication, so then I purposely build the server acknowledgement for the request inside the server. So this is the acknowledgement, but it's not requirement. For your reference, I have added that one. Basically, the datagram packet itself has the message size, and a destination address and the port. So that's the datagram. And when you are talking about the TCP, it's a connection oriented communication, right? So previously it's a connectionless, UDP is a connectionless. In a TCP, it's a connection oriented. In a TCP communication, basically, before sending any message between the two processors A and B, basically there will be a first message, there will be a initialization message which transfer between sender and the receiver in order to make the connection, right? So again I will take a drawing. Again, let's say I have A and B. We have router A, router B, and router C. So in this TCP connection, so basically there will be initialization call, or the initialization communication happen between the sender and the receiver in order to find the route, or the find a route or make a connection, right? There will be initialization call. It can be traversed through the A, C, B, or then reach to the destination B, right? So then onwards, in with the communication between the A and B, the TCP communication or TCP protocol refer the same connection or the same path or the same routing. That's why we are saying that's connection oriented communication. First in the TCP define it, find the path to communicate between the source and the destination, or the sender and the receiver. Then onwards, message will transfer in between the A and B, or the sender and the receiver, referring the predefined or the created connection or the created routing path. That's the difference. In the UDP, it's a connectionless. So basically, datagrams they are passed to the network. So then the datagram itself find a possible route and find the destination eventually, right? So then it does not prefer predefined connection or the routing path in UDP. But with the TCP, there will be initialization call has happened with the A and B in order to find a path, not the shortest path, something, right? Find some path which can reach from A to B. So that's the basic idea, right? There can be some paths which are shorter than the uh, uh, identified path. In here, we are not interested on the shortest path, right? Finding any path which can reach from A to B. So that's a making a connection. Some path, some kind of a path or the routing path where that messages can transferred from A to B. So that's a connection oriented communication, or the what happened with the TCP, right? So in the TCP, basically we had the acknowledgement as well, right? So in a TCP communication, again, they have the message size, they define the message size. And TCP protocol, it prefer the acknowledgement scheme, right? Not like the UDP, TCP itself prefer the acknowledgement, right? That means it ensure that that sender get a kind of acknowledgement from the receiver, verifying that it has received the respective content. So likewise, so TCP protocol, it refer acknowledgement. So message identifiers are associated with the IP packets, recipient data object. So some information are there, right? So so when you're talking about some issues that we are having with the TCP, basically we are having some problems in matching data items, right? when we are transferring some uh, multiple data types, right? So in advance we need to uh, in advance that receiving party has to receive or the extract the same message in the same order. If you send first, if you send the integer information and the string information likewise, so that receive receiver also has to receive that information and process that information in respective order. So that's a matching of data items. So that's a problem we are having with the TCP. And again and we will discuss. So basically we have blocking. So here we have the blocking. The data written into the stream is kept in the queue. So as we discussed with the UDP, again with the destination socket there will be a queue in order to reduce that block, in order to resolve that blocking issue that receivers will experience with the uh, blocking scenarios. So when you are looking at the TCP, so TCP basically use a checksum. So in a TCP stream, basically they use a checksum in order to ensure the integrity of the information, right? So checksum, it includes that message itself includes some information metadata related to the integrity. So that's where we use as a checksum. So in TCP, they refer checksum to validate the content. So with the use of algorithms, we can validate whether that content is uh, that the integrity of that message can be validated. So that's the idea. Or corrupted message or something. So we can ensure that we have received the actual message which are sent by the sender, right? So we can find a lot of protocols or the implementation which have refer the TCP. So you referring to TCP, HTTP protocol have introduced using the port 80 and port 443 for the HTTPS. And for the file transferring protocol, it uses port 22 and underlying protocol would be TCP with the telnet port 23. Likewise, SMTP, simple mail transferring protocol 25. So various implementation. Port 25 is kind of a by default, but there can be some other ports as well, right? So here, this is about the UDP and the TCP. And when you are talking about the objects in our processors, when you are talking about the objects and transferring object in between the two processors, we have to talk about the external data representation and the marshalling, right? It's like we are familiar with objects, right? In Java itself, we are referring objects. Likewise, let's assume that we need to transfer objects. We need to transfer object information between two processors, right? Uh, how we are going to, so in such cases, how we are going to manage that one? So that's what we are discussing here, right? So basically in a object means itself having a data structure, some kind of a data structures is managing in that process level, right? So that's the idea in object, right? It's actually a data structure. So how are we going to communicate that data structure in between two processors in that means of interprocess communication, right? When you're talking about first, when you're talking about uh, that communication, we have the main challenge would be that uh, transferring the uh, data types, right? So in when you're talking about the object or the data that when you're talking about the object, so in object we have to expect many types of data types, right? Name, if it is a person object, name could be string, but age could be integer. Again, some other information can be in the float or the double, likewise. And again, there will be challenges in platform level, like in integers there would be two type of ordering, right? Big Indian or the little Indian ordering. It's depend on the platform. Likewise, there will be couple of challenges. So then in, so when you're talking, so here we are talking about two processes. These processes can be executed in two completely different architectures on the networks or the nodes. So then how we are going to make that communication in between these two processes, right? So that's the main challenging thing, right? So marshalling is kind of a concept or the process we are talking about, assembling the data items and uh, deassembling the disassembling of that data items, right? So in order to communicate that information or the data structure through the network from between two processes, so we first do the marshalling or the assembling part of that uh, message, right? Connecting, so let us say that if we want to pass that person object from process A to B, so we have to do some for transformation. So that's the marshalling. Again, at the receiving party, so again that receiver should do the disassembling part, right? Unmarshalling. So again, construct the object referring the received message. So that's the marshalling and the unmarshalling. Marshalling, that means referring object creates the message which can transfer through that network. And in the unmarshalling, so basically receiver receive the content or the message through the network and again construct the respective data structure. That's the marshalling and the unmarshalling, right? So in that marshalling and unmarshalling, so here, so marshalling means that cre- create that data structure which can transfer through the network. So in terms of marshalling, here we have three examples, right? So initially we have the CORBA, it's a data representation, and we are mostly familiar with the Java or object serialization, right? And even we have that, we are familiar with the XML or the extensible markup languages, right? So I'm not going to discuss these three topics since I have given exercise regarding these three types, right? So here you are asked to go and research about these available representation, data representation in terms of marshalling, right? So then we can have a discussion about your findings, right? Because of that, to give you some time, I'm not going to describe these things. I believe that 2 and 3 you will be familiar with these things, right? So we have another topic, as I remember it's the last topic. So it's a multicast. So in a multicast communication, so in a previous we have discussed about the communication between two processes, right? But in a multicast, that sender will send that message to many processes, not only to a single message, a single process, right? In the previous discussion, for the explanation, we have discussed sender and the receiver. Likewise, we only think about the two processes. But with the multicast communication, sender will send that message to rest of the receivers, or send that message to not only to a one process. It is totally talking about the multiple processes. That means in the receiving end, there will be multiple processes. Right. So in the multicast infrastructure of the communication, the multicast communication is kind of a infrastructure which have mainly referred with the distributed system setup, right? So here we have 4 things, right? For characteristics. First one is fault tolerance based replicated based on replicated services, right? So it's like each node multicast the health. So as an example, every node itself multicast cast its health to rest of the members, right? So likewise, so in a distributed system, that means it has in a distributed system we are talking about many nodes or the many connected machines. Let's say we have 4 nodes interconnected in a distributed system. So this is our distributed system, right? So in a multicast system, in a distributed system, we mainly refer that multicast communication in between the connected nodes, right? So in order to provide fault tolerance setup in our distributed system, so that health of each and every node is a critical thing. So in order to communicate that health or the status of each and every node, we can refer the multicast communication, right? In terms of fault tolerance based on the replicated services, right? So basically, each and every node can share the status in between each other in a distributed system. Each and every node, there's they are multicasting their status in between every other node, right? So let's assume that this is a Hadoop distributed file system, HDFS, right? Let's assume that we have a file, right? It has distributed over AB. This file has distributed over A and B. Or say, let's say it's only available in A. We have a file A and we have uh, replicas in A and B and C. For that respective file, we in HDFS it maintain 2 replicas in B and C, right? So talking about the fault tolerance based on the replication services first thing, right? So that means in our distributed system, we are managing files in a distributed manner, right? So that means some files can contain another node likewise, right? If we look at the interested file, right, this is our interested file, right, and that some process may work on that interested file, but replicas are managing both C and D, B and C nodes, right? So let's assume that that process is updating the document. That process is doing the update on this file. Let's say it's F1, the replica of, this is the replica of F1. Right, this is file F1. That process is doing update on file F1, which reside in the node day. So in order to provide that, in order to make sure that updates are reflected on both replicas, A should multicast the updates into both A and B. So basically that node A will multicast the changes to all other nodes, and then based on the update that nodes are receiving, so they are looking at the updated file. If that file is reside in the corresponding node, so then reflect the changes. They will ignore the update then, right? This is the first one. And second one will be the discovering services in the spontaneous networking, right? So in a network or the distributed system, we continuously connecting some services, right? Let's say so we have distributed network and we are dealing with the load balancer, and so this is the application service, right? So we have one application service, and so request coming through the load balancer, and for the moment it has configured with the one application. Let's assume that in our platform or the distributed environment, we have reached up to the maximum traffic handling part. So then eventually we need to set up another replica of that, or eventually we need to set up another instance of that application, right? So now it's available in order to take the load from the load balancer, but how we are going to communicate that newly created instance between the load balancer, or there can be lot of interconnected services, right? There can be other interconnected services, right? So for your reference, I will use that single load balancer, right? Now this service has now this service is available for taking the request, and how we are going to communicate that with the other services, right? Discovering of that uh, spontaneous networking. So that's what we are discussing here. So this application can multicast perspective services. So right, so then it's why the net it's actually it's enable the network discoverability, right? So this is a new instance. So then that means it's our infrastructure has updated. So in order to discover the new updates, we can use that multicast communication. That means that node itself multicast to connected all other nodes, saying that so basically communicate that it's now appear on the infrastructure. So that's the second one. And again, so like fault tolerance, again it can provide the better performance through the replicated data, right? In the replication management, right? uh, uh, one motivation into having the replica is that providing a fault tolerance infrastructure. So maintain the replicas, that means we are going to reduce the chance of uh, failing of that service or the uh, system, right? Again, by having the replicas we can have the better performance. So think about the Google platform, right? In a Google platform they have the main servers in the US, but now they have region servers, right? So the all the updates they are done to the main servers, they have to replicate it in the region servers. And normally they have the regions based on the IPs. So basically we are not communicating. So if we just go to the google.com, basically we are not reaching the US or that main server in the google.com, right? So based on our IP range, we are actually redirect to the India or the Singapore. It's region. We are communicate with the region server, but the content are same as it is, right? So basically they are doing the mirroring, mirror. They are doing the mirroring task, right? So basically main servers they reflect the changes to the replicas or the region servers. So in order to provide a better performance, right? Rather than rather than sending the request to the US and receiving that information from the US servers, in order to make that communication more productive or the speed, so basically they are managing the replicas in the region wise, right? So then the request has served through the closest region server. So that's the third thing. So how are we going to replicate how we are going so in such infrastructure they are using the multicast communication in order to reflect the updates. So if that main server get updated, so then region it multicast the updates into the all other region servers. So that's how they are managing. And propagation of event notifications, right? So again that if you think about the Facebook infrastructure, so then instantly we can receive the status changes, right? So they can propagate the notification even. So multicast, so in that parties they will look at the message they have received, otherwise they ignore the message, but continuously propagate the notification through the multicast mechanism, right? So when you are looking at the multicast, we can see the IP multicast, right? You know IP. So by looking at the IP, uh, that information can be multicast, or based on when you're looking at the IP multicast, there are two implementation, multicast based on the routers. So then that means that message sent to the router which has configured as a multicast router, or otherwise we can define the ranges, IP ranges, right? So if you send that message to that IP range, so basically it means that that message should transfer to the all other connected nodes. right? And when you're talking about interprocess communication, again we have that network virtualization where we are talking about VPNs and all, right? Right. So basically, in overlay networks or the network virtualization, we are mainly concerned about the performance and the security, right? So when we are talking about the internet communication, so it's open, so anybody can look into that messages which are transferred in between that in within that network. So in order to provide some security, and that security mainly, so they can set up a virtual network, right? So overlay networks, so we have discussed the OSAI 7-layer network, right? So that's the so that's a 7-layer network is the base, that's the base of that internet communication. But with the virtualization, we are providing a separate network, a separate layer in addition to that 7 layers, right, which trap the content. So if we start with the message, so in a first layer, it will wrap the content. Next layer, again, it will wrap the content, right? Likewise, 7 layers, they get the message, underline message, and do the wrapping part. That means embedding the content, protocol related information. 1, 2, 3, 4, 5, right? So this is basically our message, but when you're transferring through that 7 layers, basically it's like that message get wrapped by each and every layer. But this is kind of a in internet. So when you're talking about 7-layer communication, 7 layer OSI 7 layers, that means like a standard. So then we know the protocols, we know how to extract that one, right? So that means any message which are uh, transfer in that network with that 7-layer protocols. So that means anybody can extract the message, right? So in all virtualization, basically it provides another additional layer which are kind of a particularly belongs to the that virtual network, right? It's a separate layer. Let us assume it's a banking system. So bank, they can they can set up a virtual network. So then that extraction of that underlying that content is depend on that virtual, depend on the network, right? So that's the idea. So then that message will transfer to the same network, but anybody cannot access that data since they have wrapped. It's like the content has wrapped through the custom made network layer. That's why that's why we are saying that overlay networks, right? So basically it's wrapped the underlying OCI standard packet with a custom layer. So that's how we provide the virtualization, right? So are there any questions regarding that one? I believe that it's 3 now. Any questions? Hello? Or otherwise we can wind up the session now. So I have given the exercise here. Basically, you have to research on that 3 possible data representation and marshalling approaches like COBA, Java, serialization, and the XML, right? So I'm going to wind up the session now, since you don't have any question. Thank you.